Hello, my name is Tim Campbell and this is my submission for Spatial and Photorealistic Visualization Virtual Seminar. In this video seminar, I plan on overviewing the creation process for low-poly assets ideal for game development. As the graphical capabilities of processors grow exponentially, you would think that the need for conservative 3D modeling would disappear soon. But as devices get more mobile and games get more ambitious, the need for low-cost and high-quality models is more prevalent than ever before. For this video, we will be modeling and rigging a robotic character for an RTS or third-person shooter. This method of processing power is ideal for systems with low graphical output, as well as games with large-scale environments that need to display multiple units on screen, such as Civilization, Warhammer, Halo Wars, Dota, and many more. Developing a 3D asset takes a number of stages. First off, we need to begin with a concept and idea of what we want to create. Then go on to 3D modeling both a low poly and a high poly version of the model. Then we can export those and generate baked maps based on their geometry. Once the unit is textured, then we begin rigging the unit so that it may be animated in the games. Finally, we export the 3D model so that it can be compiled into a game engine. Before I started designing my character, I looked at different references from games and movies. Specifically, I based my designs off of characters from War of the Worlds, Apex Legends, and Halo. I then created 3 variant designs which I could later reference in my 3D modeling. When it came to 3D modeling the character, I started by adding a mirror modifier to the object. This helps speed up the design process and ensures that the character is symmetrical. I start with a simple cube, and then I add loop cuts and extrusions to help shape the mesh. Because I am modeling a robotic character, it allows me to get away with using low poly edges and sharp corners. For the legs, I model them in 3 segments so that they can easily move and transform when animated. And then I duplicate them for both front and back. Next, I start with the high poly model. Usually this would come before the low poly version, but because I'm making a robotic character and want to utilize the low poly mesh to my best advantage, I simply add my extrusions and other little details that wouldn't be in the original mesh onto the pre-existing low poly. This way, the details are more likely to be successfully baked onto the low poly's texture. Also, I make sure that I keep the legs separate from the body to make sure that when I go to bake the maps that they don't accidentally pick up the body. As for unwrapping, I originally went with an automated unwrap, which broke down every single triangle into its own texture coordinate. At first this was very beneficial as it saved a lot of time on mapping, as well as keeping every polygon to a uniform scale that could still easily be read by a computer. However, a manually unwrapped character model is far easier to texture in programs like Photoshop, and an automated one is impossible to texture without using some sort of 3D software, such as ZBrush or Substance Painter. I took the effort to go back and properly unwrap the model, and as you can see, I conserved a lot of image space by condensing the 4 maps of the legs into one singular mesh. It also allows me to make proper specular maps for the character model, which is important because of the metallic material the robot is made of. After exporting both a low poly and a high poly object file, I brought them over into the free software XNormals to generate a normal map and an occlusion map. The software allows you to create your own resolution, so I went with a 4K texture, although in a real-time strategy game, the texture would be much smaller so that the system doesn't have to process as much. After the maps have been generated, I then bring them back over into Blender and assign them to their various material texture slots. Despite being the low poly model, the normal map will affect the way that the light reflects off the model, making it appear as if it has more detail. Now that the textures have been applied, I can move the legs back into their original place and then begin rigging the character. This is done by adding objects known as bones inside the mesh. Much like a real-life skeleton, these bones act as axes for which limbs can move. These bones can then be translated, rotated, and scaled to imitate real-life movement using a skeletal structure of different bones. I start by adding the parent bone in the center of the robot, then creating a network of bones to act as a leg, which I then duplicate for the other 3 legs, to help make the animations seem more lifelike, as well as save a lot of time on posing and keyframing. I add inverse kinematics to the end of the legs to help each leg segment to move as I move the foot. Finally, when I am comfortable with the rig, I then begin animating. This is done by translating the rotation, location, and scale of a bone, and assigning it to a specific frame within the animation. Since this character is going to be used in an RTS game, I decided to make 5 separate animations. idle for when the character is at a standstill and has no directions, a walk cycle for when it's approaching an enemy or moving to another location, a short ranged attack it can use when it's within range, and a death animation when it has been destroyed. Now the character is completely ready for a game development and can be easily exported into an object or FBX file and then imported through an engine such as Unity or the Unreal Engine. While obviously low poly modeling isn't ideal for a realistic render, converting high detailed objects into normal maps and then using them on lower poly models is vital for virtual reality in real-time space. As such, I plan on using this method for generating normal maps highly through my real-time renders in virtual reality, as this technique is vital for creating fluid and responsive 3D environments.